So what exactly is EDA? Think of yourself as a detective arriving at a crime scene. You wouldn't immediately name a suspect. First, you'd survey the scene, gather clues, and form initial hypotheses. EDA is precisely that. It's the process of interviewing your data to understand its main characteristics, spot anomalies, and uncover hidden patterns, all before you commit to any formal modeling. Building on that detective analogy, why is this initial investigation so critical? Attempting to build a machine learning model without first performing EDA is like constructing a skyscraper on an untested foundation. You risk building on faulty data, missing key relationships, or making flawed assumptions. EDA is your quality assurance step. It ensures your analytical foundation is solid, saving you from costly errors down the line. Before we dive into techniques, let's place EDA within the larger data science lifecycle. It's not a single step, but the iterative heart of the process. After initial data collection and basic cleaning, EDA begins. The insights you gain from EDA directly inform crucial later stages like feature engineering and model selection. But importantly, it often sends you back to refine your data cleaning, creating a powerful feedback loop. Our first act as data detectives is to identify our evidence. All data can be broadly classified into two families: numerical and categorical. Numerical data represents measurable quantities, while categorical data represents labels or groups. Correctly identifying these types is the most fundamental skill in EDA, because the type of data you have dictates every tool and technique you can use. Let's look closer at numerical data. It can be subdivided into two types. Discrete data consists of countable, whole numbers, like the number of rooms in a house. Continuous data, on the other hand, can take any value within a range, often measured, like the exact square footage of a property. Understanding this distinction helps us choose the right visualizations later on. Now for categorical data. This type also has two important subcategories. Nominal data consists of labels with no intrinsic order, like country or brand. Ordinal data, however, has a meaningful order or ranking, but the distance between ranks isn't defined. Think of customer satisfaction ratings like poor, good, and excellent. Recognizing this order is key to proper analysis. With our data types defined, our investigation can begin. We'll start with univariate analysis, which means analyzing variables one at a time. This is the simplest yet most foundational part of EDA. By examining each feature in isolation, we can understand its individual characteristics before we explore how it interacts with others. Let's begin by inspecting a single numerical variable. For any numerical variable, our first question is, what's a typical value? This is called central tendency. The most common measure is the mean, or average, calculated by summing all values and dividing by the count. The mean is intuitive and widely used, but it has a critical weakness. It's very sensitive to extreme values, also known as outliers. To counter the mean sensitivity, we use the median. The median is the middle value when the data is sorted. If there's an even number of values, it's the average of the two middle ones. The median's superpower is its robustness. It is not affected by extreme outliers, making it a more reliable measure of central tendency for skewed datasets. Our third measure of central tendency is the mode, which is simply the most frequently occurring value in the dataset. A dataset can have one mode, multiple modes, multimodal, or no mode at all. While less common for continuous data, the mode is the primary measure for categorical variables, instantly telling us the most common category. Understanding the center isn't enough. We also need to know how spread out the data is. This is called dispersion. The simplest measure is the range, calculated as the maximum value minus the minimum. While easy to compute, the range is extremely sensitive to outliers, as it depends entirely on the two most extreme points in the data. For a more robust measure of spread, we turn to variance and standard deviation. The standard deviation is the most common measure and tells us, on average, how far each data point is from the mean. A small standard deviation indicates that data points are tightly clustered around the mean, suggesting consistency. A large standard deviation means the data is widely spread out. Building on that idea of spread, we can use quartiles and the interquartile range, or IQR. Quartiles divide your sorted data into 4 equal parts. The IQR is the range between the first quartile, Q1, the 25th percentile, and the third quartile, Q3, the 75th percentile. This range contains the middle 50% of your data and, crucially, is not affected by outliers, making it a robust measure of spread. Beyond center and spread, we must also consider the shape of the data's distribution. Skewness measures the asymmetry of the data. A positively skewed distribution has a long tail to the right, often seen in income data. A negatively skewed distribution has a long tail to the left. A symmetrical distribution, like the classic bell curve, has no skew. This shape gives us vital clues about the underlying data. Now let's bring these numerical concepts to life with visualization. The histogram is the most important visual tool for a single numerical variable. It groups numbers into ranges, or bins, and uses bars to show the frequency of data in each bin. With one glance, a histogram reveals the data's central tendency, spread, and skewness, telling a complete story of the distribution. Another powerful visualization is the box plot. It provides a compact 5-number summary: the minimum, first quartile, Q1, median, third quartile, Q3, and maximum. The box represents the interquartile range, the middle 50% of the data. Its true power, however, is in clearly identifying potential outliers as individual points beyond the whiskers, making it an excellent tool for data cleaning. We've thoroughly inspected numerical variables. Now, let's pivot our investigation to categorical variables. Remember, these represent groups or labels, so our methods will change. Instead of calculating means and standard deviations, our primary focus will be on counting frequencies and observing proportions. Let's see how to summarize this type of data. The fundamental tool for summarizing a single categorical variable is the frequency table. This simple table lists each unique category and its frequency, the number of times it appears. We often add a relative frequency, or percentage column, to understand each category's proportion of the total, which is crucial for comparing distributions across datasets of different sizes. To visualize the information from our frequency table, we use a bar chart. It is the gold standard for plotting categorical data. Each bar represents a category, and its length is proportional to the frequency. Bar charts make it incredibly easy for our eyes to compare the counts between different categories, making them a clear and honest way to present categorical distributions. While you will often see pie charts used for categorical data, they should be used with caution. A pie chart represents proportions as slices of a whole. However, humans are not very good at accurately comparing angles. When slices are similar in size, or when there are too many categories, a pie chart can be very misleading. In most cases, a bar chart is the clearer, more effective choice. We've now mastered analyzing variables one by one, but the most profound insights often come from exploring relationships between variables. This is bivariate analysis. We'll investigate 3 key pairings: the relationship between 2 numerical variables, between a numerical and a categorical variable, and between 2 categorical variables. Let's start with the numerical pairing. To visualize the relationship between 2 numerical variables, like years of experience and salary, our primary tool is the scatter plot. Each point on the plot represents one observation, positioned according to its values on the 2 axes. This single chart allows us to visually assess the relationship's direction, positive or negative, strength, strong or weak, and form, linear or nonlinear. While a scatter plot gives a visual impression, we need a metric to quantify the strength and direction of a linear relationship. This is correlation. The Pearson correlation coefficient, denoted as R, ranges from -1 to +1. A value near +1 indicates a strong positive linear relationship, -1 indicates a strong negative linear relationship, and 0 indicates no linear relationship. This brings us to the most important mantra in all of data analysis. Correlation does not imply causation. Just because two variables are strongly correlated doesn't mean one causes the other. There might be a third, lurking variable influencing both. For example, ice cream sales and drowning incidents are correlated, but the cause is a third factor, hot weather. Next, how do we compare a numerical variable across different categories? For this, we use grouped visualizations. Side-by-side box plots are excellent for this. By placing a box plot for each category on the same scale, we can instantly compare their medians, spreads, and identify outliers within each group. This is perfect for answering questions like, do salaries differ across departments? Finally, to analyze the relationship between two categorical variables, we use a contingency table, or cross-tabulation. This table shows the frequency for every combination of categories. To visualize it, a stacked or grouped bar chart is effective. This allows us to see how the distribution of one variable changes when conditioned on the other, revealing potential associations. Sometimes, looking at just two variables isn't enough. We need to enter the realm of multivariate analysis to examine 3 or more variables simultaneously. This is where we can uncover more complex interactions. For instance, we can enhance a scatter plot by using color or size of the points to represent a third or even a fourth variable. A fantastic tool for multivariate visualization is the pair plot. It creates a matrix of plots where every numerical variable in your dataset is plotted against every other. The diagonal typically shows a histogram for each variable's own distribution. By coloring the points based on a categorical variable, you get a powerful, high-density summary of your entire dataset in one graphic. Another essential multivariate tool is the heat map, which is perfect for visualizing a correlation matrix. It uses color to represent the correlation values between all pairs of numerical variables. A dark color might indicate a strong positive correlation, a light color a strong negative one. This allows you to spot highly correlated variables at a glance, which is crucial for tasks like feature selection. A powerful side effect of our exploratory journey is that it's the best way to diagnose data quality issues. EDA isn't separate from data cleaning, it drives it. The visualizations and summaries we've discussed will naturally expose problems like missing values, strange outliers, and other inconsistencies that must be addressed before modeling. One of the most common issues is missing values. Our EDA will show us which variables are affected and to what extent. We then need a strategy. Should we remove the rows with missing data? This is simple but can discard valuable information. Or should we impute the missing values by filling them with the mean, median, or a more sophisticated estimate? The best choice depends on the context and the reason the data is missing. EDA is also our best tool for detecting outliers, data points that are significantly different from others. Box plots and scatter plots make them visually obvious. Once identified, we must investigate. Is it a simple data entry error? Or is it a genuine, rare event that contains valuable information? The decision to remove, correct, or keep an outlier can dramatically impact our analysis. Beyond cleaning, the insights from EDA are the fuel for feature engineering, the process of creating new, more informative variables from your existing data. For example, if your EDA on a time series dataset reveals a weekly pattern, you might create a new Day of the Week feature. If you see a skewed variable, you might apply a log transformation to make patterns more apparent. EDA tells you what to build. To perform all this analysis, we use specialized tools. In the Python ecosystem, Pandas is the workhorse for data manipulation, while Matplotlib and Seaborn create our powerful visualizations. For those in the R community, the tidyverse, including packages like dplyr for manipulation and ggplot2 for visualization, provides a complete and elegant toolkit. Ultimately, the goal of EDA is not just to create charts and statistics, but to build a narrative. This is the art of data storytelling. Your analysis should tell a clear and compelling story about the data, guiding your audience through your discoveries, highlighting key insights and leading to actionable conclusions. A good EDA report is a story supported by evidence. As we conclude, remember that EDA is not a linear checklist. It's an iterative, creative cycle of curiosity. You start with a question, you visualize the data to find a clue. That clue leads to a deeper question, which might require you to clean or transform the data, leading to a new visualization. This loop of questioning and discovery is the true mindset of an effective data explorer. Congratulations! You've just journeyed through the entire landscape of exploratory data analysis. From data types and univariate summaries to complex relationships and data storytelling, you now have the framework to approach any data set with confidence and curiosity. Your next step is the most important one: practice. Find a data set that excites you and begin your own investigation. The story is waiting to be told.